We're almost ready to move on from sorting problems, but there's one more loose end that I want to tie up, and it's related to these two problems. So the first problem is called median. And in the median problem, I give you an array A of, there's that word again, comparable values. And all I want from you is to tell me which element would show up in the middle of the sorted order. Okay, fine. So I admit that if you're familiar with medians from statistics, this is not the same definition of median that you would use there. This problem can easily use that definition without changing really anything. Like, ultimately, the complexity of our algorithm will be the same. However, for the sake of this lecture, just to make sure we always have a specific index that we're talking about, we'll define the median to be at the thing at index n over 2. And if n over 2 is not an integer, then just truncate it down to an integer with the floor function. So that's the median problem. I just want one element of the sorted sequence. Now, the median problem is sort of a special case of this more general selection problem, where I give you an array of comparable values and some index k. And all I want from you is to tell me which element would show up at index k if you were to sort the sequence. So, hopefully it's clear that these do feel a bit like sorting problems. In fact, they seem so similar to sorting problems that I already have a pretty good idea for an algorithm that might work to solve the selection problem. It's this one. There we go. And so I purport that this procedure will give us the right answer for selection. You give me an index k, so what I'll do is I'll just sort the array A, and then I'll just return to you the thing at position k. Okay, problem solved. And because median is actually a special case of selection, so I can solve median by just calling selection with the index floor of n over 2, well, then I guess I've solved the problem. Great. Okay, and it's even better. I've solved it in n log n time because I know this sorting step can be done with merge sort, which we know is worst case n log n. So we're done. Okay, we can move on from sorting. Okay, the problem is, you know me, I can't end a lecture at slide 3. We're going to be here for an hour one way or another. We're going to talk about something. So I guess the question is, okay, we've got an n log n algorithm for selection, but can we do better? So that's the usual question. And I think the answer sort of has to be yes. And I don't really have a good explanation for why I think that. It just feels like the selection problem is easier than sorting. It feels like if all you want is one element of a sorted sequence, shouldn't that be easier than getting the entire sorted sequence? It just feels like that's an easier problem. Okay, now nobody takes you seriously in math if you say that something feels like there should be a better solution. So instead I'm going to say, intuitively it seems like selection should be a fundamentally easier problem. Now those are the kind of words that get you recognized in math. Intuitively, well, I want everybody to know about my great intuitions, especially about fundamentally easier problems. So it just seems to me as if selecting one element of a sorted sequence, there has to be some way of avoiding the full work of sorting the entire sequence. Sure, I have to do certain sorting-related tasks, but I shouldn't need to generate the entire sorted sequence, and that means there has to be a way for me to save some time. Now we know, as usual with algorithm design tasks, that just because I can find a faster algorithm doesn't mean that it's asymptotically faster. So maybe I can work on this problem for a while and come up with an algorithm that does less work, but then it turns out that the algorithm I come up with is still, just like this one, big theta of n log n. Well, that's too bad, but I think it's at least worth a try, to try and find something asymptotically better than n log n. It's also reasonable that I can't do too much better, because if I give you a sequence of n things, well, logically you should have to look at all of them before you can tell me anything about what shows up in position k. That is, if I add just one more element to my sequence that you've never seen, that could alter the position of everything that I'm interested in. So I guess logically you have to look at every single element before you could solve the selection problem. Which to me says that the selection problem requires big omega of n operations in the worst case. Sure, maybe there's some algorithm out there that could answer the question in less than n operations in some cases, although that seems a little bit unlikely. But certainly you'd have to look at n things in the sequence in the worst case. There has to be some case where it inspects everything. Notice that I defined both of the problems with that word comparable. That is, I defined them to work within a comparison framework. I don't allow you to assume anything about the contents of the array A besides that there is this comparison operation. In other words, I'm not allowed to short-circuit my earlier algorithm and, for example, use something like bucket sort or radix sort for that. So obviously, I talked about this step as requiring n log n time because we're using a comparison framework, and the best comparison sorting algorithm that I know about is merge sort, which is big theta of n log n in the worst case. If I were allowed to assume more about the contents of my array A, so I was allowed to use non-comparison based methods, then perhaps maybe I'm lucky and I could employ bucket sort or radix sort, and that would bring the running time down. And to be clear, now we can't always, when we use radix sort, we can't always be assured that it's going to be linear time, but suppose I were able to use radix sort and make sorting a big theta of n operation. Well, if I knew that was the case, then I guess it wouldn't be worth it to pursue a better algorithm for this, because that would mean that this whole procedure is big theta of n, and I was able to assemble it with off-the-shelf components like radix sort. So that's already, I think, as good as I could get. As I said earlier, although I haven't written a proof of this, I think that there is strong evidence that we can't solve selection in general in better than n operations. So I guess what we're doing is we're looking for an algorithm that sits somewhere between n and n log n. Although we don't want one that is n log n. We want anything that is less than n log n all the way down to n. Okay, so I think about a problem like this, once we've narrowed it down to this case, and I'm thinking, okay, I really hope we can find a big theta of n algorithm, because if the best algorithm we can come up with is in between somewhere, then I don't really want to work with that running time. Like, what running times can we think of that are strictly between n and n log n? There are plenty of them, and some algorithms do exist with those running times, but they're sort of weird. So for example, I could end up with an algorithm that's n log of log n. Ugh. I mean, and I wonder, I don't want to see that recurrence. I don't want to work with a recurrence that results in this running time. I'm sure such a thing exists, and I'm sure it's very nice, but I would really rather not analyze that algorithm. So I sort of hope we end up with something linear, because just, I don't know, to save time on analysis, as well as, I suppose, for the global good, it's nice to have fast algorithms. Okay, so here's my first idea, and maybe this might have come to mind for you as well. This is clearly a problem that is intimately related to sorting. I mean, obviously, because my algorithm to solve it could just sort the array and return one position. And I'm even using a comparison-based framework. It's pretty clear this is a sorting adjacent problem. It's a very close relative of sorting. So how about this? Why don't I just go look at my comparison sorting algorithms and see if I can find one that I could adapt? So I guess my intuition for this is I don't need to do the full amount of work for sorting to solve this problem. Why not take a sorting algorithm, deconstruct it a bit, and see whether I can strip away certain components of it while still getting the right answer? So that brings us back to our character select screen. Now, for logistical reasons, because we don't know what heap sort is yet, I'm going to make the executive decision and just declare that heap sort isn't going to end up helping us. It actually turns out that I could use heaps and heap sort as the basis for a selection algorithm that would be better than some of the possibilities, but actually the algorithm we end up creating at the end of this lecture will be better than what heap sort could give us in general. So I'm just going to rule heap sort out because we don't know what heap sort is yet, and if we had to know what heap sort was, obviously I'd just be giving this lecture a bit later in the sequence after we learned about heap sort. Similarly, obviously we can cross off radix sort, because we must be working with a comparison-based algorithm. And that leaves the two pairs of algorithms that we saw back in lecture 9. And you can see I've already sort of, again, this is just by intuition. So in one of these design tasks, we just have to use our instincts to try and figure out which avenues are most likely to lead to some success. So which are the best leads, I guess. And I've already, the slide has already intuitively, I guess, ruled out two things. And I will justify my logic for that, but I can give a high-level explanation. So we have these two pairs of sorting algorithms, insertion selection and quicksort and merge sort. And we saw in lecture 9, or at least I strongly advanced my point of view, that these two pairs are closely related. They're sort of siblings. Insertion sort and selection sort are basically leveraging the same insight, but in opposite ways. And same thing with merge sort and quicksort. And there are lots of other selection-based algorithms and lots of other divide and conquer algorithms, so these things are part of a large family. But certainly I think insertion sort and selection sort are dual to each other. They sort of do, they have a lot in common to the point of almost being mere images. And you can see I've ruled out insertion sort and merge sort because basically both insertion sort and merge sort don't really fix the final position of any elements until relatively late in the process. And so it shouldn't surprise us, as we'll see in a few minutes, that selection sort and quicksort sort of do, because they're the opposite mirror image in a sense. They do a lot of their work early in the process. So it's strange because merge sort and insertion sort of their respective pairs are the faster algorithm, but there are certain disadvantages to their technique as far as adapting them to other things. So I'll talk about what I mean about insertion sort and merge sort not seeming like good avenues to pursue. Let's think about insertion sort first. So suppose I'm near the end of insertion sort. I'm just before the step where I insert the last element. So here's my sorted sequence here. Notice that when I finally insert negative 99, it's going to show up at the beginning of B, which means the position of every single element already there is going to shift over by 1. I guess what this tells me is that if there was any hope that I could terminate the algorithm early and come up with the correct element in a certain position, it doesn't seem like that's very likely with insertion sort, because even the very last step could modify the position of every single element. So I'm going to rule it out for that reason, because obviously by the time we get to this step, I've already done n squared work, and therefore it's unlikely I'm going to be able to adapt this algorithm easily to something that requires around, n operations. Also, I am going to, I guess, adopt a harsher standard for insertion sort, because if we look at the running time of insertion sort, it's n squared. And to improve on my earlier attempt, I need to get below n log n. So I've got a lot of ground to cover if I want to improve insertion sort. So I'm going to rule that out. Now, to be clear, I'm not ruling it out formally. I'm ruling it out intuitively, by instinct. It could turn out that I could waste a bunch of time trying all the other algorithms and realize only after days of trying that actually insertion sort leads me to a perfect algorithm. I'm just ruling it out because from the algorithm design point of view, it doesn't seem to have much working in its favor, but I reserve the right to come back to it later. I'll also observe that there are certain assumptions I can make about insertion sort. So while it's true that I can't assume, unless I've inserted every element, if there's still an element left to insert, obviously I can't assume that 187 is in its final position, but I can say certain things about 187. So I can say, for example, that it doesn't matter what this next element is, 187 is never going to move to the left. That's never going to happen. At worst, it moves over to the right, but I'm never going to insert something such that it gets pushed in the opposite direction. So there are certain aspects that I can conclude based on the current ordering of the sorted sequence. It just doesn't seem like enough for insertion sort to be the right option. What about merge sort? So with merge sort, similarly, the final position of elements do not seem to be fixed until that very last merge step, right before merge sort finishes. So once all of the recursion is finished and we're doing that final merge. So for example, if I was sorting an array of size 8, that final merge would be reconstructing the array of size 8 from arrays of size 4, that last merge step. Only then does the final position of any element get fixed. And notice we saw in lecture 9 that there are lots of ways the merge could go. We could end up shuffling the two arrays together sort of alternately, like, element 1 or array 1, array 2, array 1, array 2. In this case, strangely, and this is a completely valid case, of course, we ended up actually sticking all of array 1 sandwiched between the two halves of array 2. Hopefully you can see, or you can convince yourself that unless we, know quite a bit about the structure of those two arrays, which we generally don't, we can't really assume that any particular element of array 1 ends up in any particular position in A. There are certain assumptions we can make, certain things we can deduce, but it just doesn't seem like enough. So merge sort's problem, like insertion sort, is that it does most of its work in sort of the second half of the algorithm's operation. And that means by the time any element's final position is known, or by the time we can say anything really about any element's final position, too much work has already been done. We're probably already past n log n operations. Now, I will try and say some nice things about merge sort while we're here. There are certain things I do know about elements even before recursion returns, so let's look only at A1. Suppose I don't know anything about A or A2. I'm just down the branch of recursion that computed A1. Or even further down, like I could be, halfway into A1 or something, but let's just look at A1. Look at the element 17. Can I say anything about where 17 is going to end up in A? Well, yes, but not very much. So I know that there are 17 is appearing at index 2 of A1. And I know that means 17 has to appear at at least index 2 of A, because obviously there are two things less than it, and they're still going to be less than it when I put them back into A. Similarly, I know that 17 cannot appear at the last index of A, because 187 is greater than 17. So obviously 17 has to be set back by at least 1. But that's not enough. All that lets me do as far as A is concerned is say 17 has to appear somewhere between these two positions. And that doesn't seem to be enough for my purposes, especially because even to get to that conclusion, I already have to have had done a huge amount of work. Okay, so I'm going to rule out insertion sort and merge sort. Not that maybe there is some way of adapting them, but it just doesn't seem like it's likely. So we'll just rule those out and try the other two. So both selection sort and quicksort give us a couple of reasons to be optimistic. It turns out, actually, I'll spoil it, we're going to end up looking quite a bit at quicksort. But I will show off that selection sort does have a couple of advantages of its own. But just like with insertion sort, I have to adopt a sort of harsh standard for selection sort because its running time is n squared. And I need to do better than n log n, which means, the bar is pretty high for selection sort to help me out here. So let's take a look at selection sort. With selection sort, as we know, we walk through the array from left to right, and at step I, so for example, suppose I want the value, the element of the sorted array at index 3. At step I fix the final value in position I, at the end of step I in selection sort. That means if all I care about is index 3, or in general index k, I only have to run selection sort until it gets to index k. And then I don't really care what happens with the rest of the stuff, because all I care about is this one index. And so there is some logic there that means I can end selection sort early. It's pretty easy to show that. I can end selection sort early and still get the right answer. So that's some progress. That shows me that maybe I can avoid a few operations, enough maybe to speed up selection sort, although the bar is still very high. So here's some pseudocode that I've adapted. This is just the original iterative selection sort algorithm from lecture 9, except that I modified the outer loop. That's it. Everything else is exactly the same. Because everything is the same, I'm not going to bother doing a full analysis because I think we can just duplicate most of the analysis from lecture 9. Remember that although in the implementations that I'm talking about here, I am apparently just modifying the elements of A. I guess this is where the modification is happening. And that's fine because I'm just illustrating an algorithm. In practice, if you were writing code in a programming language, maybe you're concerned that unlike a sorting problem where the caller expects the algorithm to modify the array, the caller doesn't want their array to be modified here. That's an implementation concern that we don't care about with pseudocode. So it's valid for me to modify A because we could always just declare that, A is being passed by value, or that you could make a copy of A. Remember that if you are concerned about somebody modifying your array, and you were to, before the algorithm starts, so above line 2, just make a copy of A and modify that, making the copy is big theta of n. And because the algorithm we're looking for is no faster than n, adding an extra big theta n operations won't change anything. So that's why I'm just ignoring this business of whether we're allowed to modify our input array or not. So this algorithm performs k iterations of the outer loop of selection sort, which is enough, as I showed a minute ago, to identify the final element in position k of the sorted array. And then it just returns that element. And that's it. Otherwise, it just performs k passes of an ordinary selection sort. It turns out if we were to analyze this, basically, so just to do it at a high level, the inner loop, we do end up determining that the number of iterations of the inner loop over all iterations of the outer loop still ends up being sort of, n-1 plus n-2 and so on. And therefore, the ultimate running time is just a big theta of n times k. Now, it might be n-1 times k or something, but remember that it's still basically n times k in that case, as far as big theta is concerned. Okay, so what can we say about n times k? That's certainly better than n squared, but it's still not going to be good enough for our general case. So suppose that I always want to get position 15 of my sorted array. It doesn't matter how big the array is. So it's got size 20, it's got size 40 billion. I just want position 15. What I'm really saying is, in that case, k is a constant, and which means if I only want position 15, that I actually have just derived my linear time algorithm, the one that I wanted. But that isn't realistic because k is one of my input parameters, so it could be anything. If k is equal to n-1, for example, if I always want position n-1, or to disguise this a bit better, maybe position n-15, well, then this ends up being n squared, because obviously n-15 times n is n squared, or big theta of n squared. And so I sort of have an issue here. Now, the slide quite helpfully points out that this will be better than n log n as long as k is less than n log n asymptotically. So if k is smaller than n log n, so strictly smaller, so I actually get a rare opportunity here to use little o, then this will end up being better than n log n. But that isn't really reasonable because we know that log n is not a very big number, and therefore for k to be smaller than log n doesn't really give us much real estate to work with. And of course, in general, k can be any index. So this algorithm just isn't good enough. It is going to be n squared in the worst case if I think about the worst possible choice of k. Well, too bad, but selection sort's still a nice algorithm, and as I said before when we talked about selection sort, there are benefits to using it because it's so simple and because, as I said, if you do have a case where k is constant, this actually is a pretty easy algorithm to implement and it would give you linear performance. The problem is we don't, in this case, assume that k is constant. Actually, I'll also put a bookmark here because what we're going to end up with at the end of this lecture is an algorithm that does better than this in general, but the algorithm we end up with is pretty complicated. I mean, it's hideously complicated. And that means if k is constant, you definitely would rather use this one. So what about quicksort? We've ruled out everything else, and because, I don't know, you can sort of already assume I'm going somewhere with this, I guess quicksort's going to be our choice. So why is that? Well, let's think about what quicksort does. Unlike merge sort, which does most of its real sorting work on the sort of back end of the algorithm after recursion returns, so merge sort recurses all the way down to split and then comes back up and does merging, by which time it's already done n log n work. And then, only then is it actually figuring out the sorted position of anything. Quicksort has the opposite arrangement. As we know, the merge step of quicksort is really easy. The merge step is just concatenation. It's the split step where real properties of the sorted data are determined. So let's hypothetically think about a situation where I've got an array n where n is equal to 10. And suppose that I want to figure out what element is going to show up in index 7. And I apologize in advance, my drawing is not going to be to scale, but I've got a nice typeset version in a minute. Suppose that I choose a pivot of some kind, and we're going to spend a lot of time today thinking about pivots. Suppose I choose a pivot and I perform my split operation. And I discover that when I'm done splitting, L contains 2 elements, E, so that would be the middle, which contains the pivot, also has 2 elements. And then, of course, because there are 10 elements in total, G must contain 6 elements. Okay, so I know that. The question I have is, do we care what I do with L and E? So let's think about when I'm done sorting, what are the indices I'm working with? Well, regardless of what I do inside of L, the first index of L when I'm done sorting will be index 0. And the last index will actually be index 1. There's only 2 elements in L. Similarly, E will contain index 2 and index 3. Okay, so the first index of what will become G is going to be index 4 when I'm done. And of course, in quicksort would then be sorting recursively, sorting G and sorting L, and then mashing them together with my concatenation. But now I ask the question, hey, wait a minute, isn't it true that if I just want index 7 of my result, so I'm going to move this to make my drawing, to clean my drawing up a little bit. If I just want index 7 of my result, isn't it true that it has to show up in G? Because I know that regardless of what I do inside L and E, L is always going to occupy indices 0 and 1, E is always going to occupy indices 2 and 3. And that's just based on the size of L and the size of E. I don't care what the actual elements are, I just care about the size. So basically what I'm pointing out here is I don't need to look at L and E at all. Once I know their size, I know which component will contain the thing I'm looking at, and it's going to be G. And even better, I even know, suppose I were to sort G, I actually know where the thing I'm looking for is going to be. So if I just index G directly, so there's index 0, there's index 1, there's index 2, there's index 3, if I want index 7 of my original array, I could just go and say, give me, using the selection algorithm, so using, I guess, the same process recursively, I could ask for index 3 in the sorted version of G. Okay, where did I get 3 from there? Well, I mean, I just drew it out, but it's 7 minus 4 because, and that would be, just to be clear, that's 7 minus the size of L minus the size of E. So I know I'm going into G here, and then I can just figure out the index. I can make the adjustment to the index for the size of, based on the size of L and E to get into G. And then recursively find the thing at index 3 were I to select from G. That's a big deal. And quicksort, because the split step happened so early, all of what I just discussed happened before any recursion took place, on the split step of the very first iteration of quicksort, right when I call it for the first time. That's a big deal. And so, in general, if I want index k, all I need are the sizes of L, E, and G to figure out whether index k is going to be in G or index k is going to be in L. Or if I'm really lucky, index k might lie inside of E. That's a big deal. So I could use this. I could use quicksort as the basis of a selection algorithm. And the idea basically is, unlike quicksort, which recurses into both subarrays, both L and G, in this case, I only have to recurse into the subarray that contains the thing I want. So in this case, I would recurse only into G. But there's a symmetric case where I recurse only into L. And if we do that, we end up with an algorithm called Quickselect. And for a lot of reasons, I mean, we're savvy enough to figure this out, but if the algorithm already has a name, well, then I suppose it is going to end up being sort of a big deal. So adjusting quicksort for the selection problem produces an algorithm called Quickselect. I'm going to go over it at a pretty high level because most of it is pretty similar to quicksort, and you'll see that I've written pseudocode that's a bit condensed because we already know what quicksort looks like. Okay, so the first thing is, as a base case, if you give me an array of size 1, well, here's an array of size 1. It's got only one index, and that index is 0. It's assumed, because the selection problem, if we were to scroll all the way back to the selection problem definition, it tells us that k has to be a valid index. Always. So the problem is not valid unless k is valid, which means if you give me an array of size 1, automatically k has to be equal to 0. So I'll just return a0 and we're done. That's the base case. It's easy to select one element out of a one-element array because by process of elimination, there's only one element to select. Now otherwise, if we're not in the base case, I choose a pivot. Oh, there's that line again. A pivot value from A. So I don't even tell you what the pivot is because we know that there are different options for pivoting rules, and we are going to have to fixate a lot on line 5. It turns out that choosing a good pivot rule will end up being the crux of our analysis. For our algorithm to be fast, we need to finally tackle the problem of, what is wrong with quicksort? I mean, okay, we know what's wrong with quicksort. Its running time is n squared. Okay, fine. I guess my question is, what is quicksort's problem? Why can't we get good pivot values? Well, we're finally going to try and address that problem, and we're going to get a result. I don't know if it's the most satisfying result, but it'll be a result. Anyway, otherwise, we choose a pivot via some mechanism. I then perform the partitioning step, which I've just condensed into one line because I think it's clear. We know how to do that by now. And then I use the lengths of my different pieces, L, E, and G, as the basis to figure out which of the different pieces to recurse into. So I'll sketch this. This is going to be, I'll just warn you up front, it's going to be a terrible drawing. But here's L, here's E, and here's G. And they're not internally sorted, but we know that in the sorted representation, everything in L will come first, then everything in E, and then everything in G. So what I do is I observe the first index of L is 0, and the first index of E, so the index 1 past the end of L, will be index length of L, using 0-based indices. So if k is less than length L, that means I have this situation. K is sitting somewhere inside of L, which means all I have to do is select the kth largest thing, or kth smallest thing in L. So I just recursively call Quickselect with L and K. There's no need to adjust the indices because the thing at index K of the big array will be the thing at index K of L. Okay, the next case is, suppose that I'm sitting inside of G. So suppose K ends up inside of G. Well, the first index of G is the index 1 past E. So that would actually be length of L plus length of E. And that means that if k is greater than or equal to that value, well then k is in G. Now in this case I have to adjust my index. So index 0 of G is this index of the big array. So what I do to adjust my index is I'm going to call Quickselect recursively on G. I'm going to ask for the thing at index k minus this thing. So it would be k minus length L minus length E. Okay, and then there's a third case, which, I mean, if we're lucky, we can use, but unfortunately, we sort of know in advance our worst case analysis will never actually hit this case. What happens if k is actually in E? I erased my diagram there. Okay, we'll get that back. So if I think about the case where it shows up in E, well, the first index of E, as I showed off earlier, is length L. And that means if I end up in the else, I guess I have to be inside of E, so k is somewhere here. So what I do is I just subtract off length L, and then I just return that element of E. Now, E is a sequence, and so I can return any element of it I want. I don't have to call Quickselect because everything in E compares as equal. And we know from talking about this a couple of lectures ago, and actually discussing the problem of stable sorting in the last lecture, that it might be the case that everything in E literally equals P, that it's the same value. But remember, just because two values compare as equal doesn't mean they actually are identical. That's why I'm bothering to go and get a specific element out of E. I could, if I knew I was working with, let's say, integers or something, I could just return P here, but that's not an assumption I'm allowed to make in general. So in the general form of the algorithm, I return a specific element of E. Now, because Quickselect, as we can see, if I look at this, these are three mutually exclusive cases, which means I am obviously doing recursion, but only one recursive call ever gets executed, at most. But of course, in the worst case, we should assume it always does. And so unlike quicksort, which recurses on 2 subarrays, this one recurses on only one of them. And that, I think, gives us some intuition. So I have to use that word again because we don't have any proof yet. There are reasons to be optimistic that this will be faster than quicksort. Now, as we know, quicksort itself is n squared in the worst case. So this has to be quite a bit faster than quicksort to be faster than our earlier attempt, which just used merge sort. However, we're going to have some bad news pretty quickly here. So let's think about a worst case situation. In the worst case, of course, we never get into here. We never are lucky and end up recursing into E or pulling a value out of E. Instead, we just keep recursively calling Quickselect until we get all the way down to the base case. Additionally, we have to assume the worst case situation is that we always recurse into the larger subarray. So certainly, if we end up with a situation like this where L is tiny, and G is huge, it would be great to recurse into L, because it means we're definitely going to be done with our problem quicker because there's less of L to process. However, in worst case analysis, we already know this, we have to assume that we just have the worst luck possible, and that means we always recurse into the largest subarray. And this is going to be a problem. So the way I'm going to characterize the recurrence for the worst case is we'll define a value n sub r, which is, I guess the r stands for the recursive case, and it'll be the largest size of the 2 subarrays. So whichever of L and G is larger. And I hope you can recognize early on that really L and G for our purposes, for analysis reasons, are sort of interchangeable. Like it doesn't matter whether everything goes into L or everything goes into G, we recurse into whichever one of those is larger. So the running time ends up being modeled by this recurrence here, which is one of the usual form of recurrence that we've worked with recently with sorting algorithms. And so we've got some constants, and we've got one recursive call and some linear time stuff. We already know, though, that in the worst case, if we choose a bad pivot every single time, then one of the 2 subarrays is going to be empty, and the other subarray is going to have everything else in it but the pivot. If the pivot doesn't appear more than once, that means that the largest subarray has size n minus 1. And this is bad news. So I'm not going to bother solving this recurrence. We're going to see a proof at the end of this lecture of the final result, but many of the results we come to along the way, we don't, well, in practice when you're designing algorithms, you don't have to write a proof of everything that you think about unless you finalized your result and you want to show it to others. It's good to sort of work out the beginning of a proof to make sure you're on the right track, but it's also good as an exercise if you're practicing with recurrences. This is a good recurrence to play with because we haven't seen too many recurrences of this particular form yet. But it actually turns out this actually is n squared, unfortunately. So even though we are definitely doing less work here than quicksort, it turns out this is still n squared. And if we go back and look at the quicksort analysis, it's not that surprising because when we did the quicksort analysis, the recursive case looked like this. So the number of elements in L, the number of elements in G, we recurse on both L and G, and then we've got the linear time stuff. And we notice that in the worst case, let's say L ends up having size n minus 1, which means G has size 0, which means this just ends up becoming the base case, and we just cancel this and call it CB. And so the recurrence actually does boil down to something pretty similar in the worst case of quicksort. Even though there are 2 recursive calls, one of them just sort of gets cleared out. And so this is n squared. Okay, well that's too bad. Do we give up though? I mean, earlier I ruled out selection sort because it was n squared, and I've ruled out insertion sort because it seemed like I couldn't make it any faster than n squared. And it didn't seem like merge sort could help us very much, but certainly merge sort is the best candidate we've seen so far. So shouldn't I follow my own rule here and say, oh, it's n squared, we're done? You know what? No. And the reason is this. With selection sort and insertion sort, yes, they were n squared, and yes, that's not a very good running time compared to n log n, which we already have. But both selection sort and insertion sort didn't seem to have any knobs that I could turn, any parameters I could tweak. Versus Quickselect, where if I stare at it, there is one glaring issue, which is this line 5. This is a bit of an unknown. We already know that we could choose a pivot value in a simple way, and if we did, we end up with an n squared algorithm. But this is a deliberately unknown quantity. There are maybe other pivot rules out there. So we have an algorithm that's n squared, but that gives us some hope. And maybe if we can adjust line 5 the right way, we can improve it. Maybe make it n log n, maybe make it better. So because of that unknown, I want to experiment a little bit more with Quickselect. Okay, so the worst case of Quickselect with a basic pivot rule like choosing the first element is n squared. Okay, that's bad news. for the sake of making myself feel better, let's, I don't know, like, I'll just go to my happy place and let's think about a fantasy world where everything always comes up my way. And suppose that we could guarantee that the best pivot was chosen at each step. Now, this isn't going to go anywhere formally because we can't guarantee that. We already know that. We know that with worst case analysis, obviously we could choose the worst pivot at every single step. But suppose that wasn't true. Suppose we could always guarantee the best pivot. And we did this for quicksort too, but let's just mull this over. So if we did that, then both of the two subarrays would have size about n over 2. Actually, like, we know that the pivot has to, we know that we eliminate the pivot and there are n-1 elements left to partition. And that means if we split them evenly, then each subarray will have size n-1 over 2, which is less than or equal to the floor of n over 2. And so this could have a floor function here, but because we're living in the fantasy world, in my happy place, there are no floor functions in my happy place. And n over 2 is greater than the floor of n over 2, so this recurrence would still be viable if, this fantasy were true. Now, we can actually show, if we do repeated substitution or use the master theorem or something, using any of our usual techniques, we can actually show that t of n is actually big theta of n in this case. So with quicksort, the best case scenario, we end up with a recurrence that's 2 times t of n over 2. And in that case, it would be n log n. And we know that that's also not generally feasible. We can't assume that's going to happen. With Quickselect, we only recurse into one subarray, and so there's only one recursive call, and it actually turns out that t of n is big theta of n. This is a good exercise to try. I mean, external to our analysis of Quickselect, just to make sure, as a good reinforcement of solving recurrences, try it out. It's not a very unpleasant recurrence to solve, and verify that it's big theta of n. We don't see this kind of recurrence that often, although literally as I said that, I remembered that this is the same recurrence we might see for binary search, so you can see I've already forgotten a couple of things from the last few lectures. So what we've observed here is that based only on the mechanics of pivot selection, if we're unlucky, we get n squared. If we're lucky, we get n. And I think, okay, we want an algorithm that is somewhere between n and n log n. And this diagram is not to scale. N squared is definitely quite a bit bigger than n log n. And I think, okay, I can get n if I'm really lucky. I can get n squared if I'm really unlucky. Maybe if I do just a little bit more work and come up with a clever pivoting scheme, I can guarantee a pivot that is just good enough to give me n log n, right? I mean, I don't know if I can get all the way to n, although spoiler alert, I can, but maybe I can get to n log n. So that's my thought, that it seems like based only on the pivot, I could be somewhere between n and n squared. So let's think about this. In the worst case, I end up with n squared. So in an imperfect world, in the least perfect world, I'm at n squared. In the most perfect world, I'm at n. So if the worst pivot is chosen, then I get n squared. If the best pivot is chosen, then I get n. What if I try and split the difference? So suppose I can guarantee that a sort of lousy pivot, a mediocre pivot, is always chosen, resulting in a partition where each piece contains at most 90% of elements. So there's never going to be a case where one piece contains, like the size of L will never equal n-1. At worst, the size of L will be 90 over 100, because that's 90% of n. So that is still a lot. That's way more than n over 2. But suppose I could guarantee that 90% of elements end up in each piece, at most. Which means what I'm saying there is that the size of both of them is always guaranteed to be at most this. Not at the same time, obviously, but in the worst case, the largest one will always be less than or equal to 90 over 100 times n in size. I want to analyze this. I want to see what happens if I choose a mediocre pivot. Additionally, there's nothing up my sleeve here with this 90%. That's a made-up number. I could do the same analysis, and I'm actually going to comment on this. I could do exactly the same analysis for, suppose I can guarantee that it's 60%, or suppose that I can guarantee that it's 99%, or suppose that I can guarantee that it's 99.9%. It's just some random number. I'm just choosing a number that isn't n over 2. So if I can guarantee that each subarray has size at most 90% of n, or maybe 95 or 99%. I just want to see what happens. I want to see how bad the problem is. And what we're actually going to see is that we have quite a few reasons to be hopeful here. Okay, so if at most 90% of elements are always added to one subarray, well, then the worst case is that we always get a subarray with 90%, because we know that a better split, like 75-25 or 60-40, is good for us. So if we're really unlucky, then every single time we get the maximum size of a subarray, so 90%. If we can guarantee a pivot that's always, so actually, I guess I should add, what I'm saying here is that the pivot is less than n over 10, or sorry, I shouldn't write it this way. P is less than n over 10 things. That's essentially what I'm saying. So 10% of things are less or greater than P, and 10% of things are less than P. Because that means that both L and G will contain at most 9n over 10 things. That's sort of what I'm concluding here. And I have to assume in the worst case then that we have as skewed a distribution as possible, and that means that we end up with this recurrence. So we say every single time one of the two subarrays has size 90% of n, let's try analyzing this. It turns out that T of n is actually linear in this case. Even if the split is bad, so 90%, 10%, or even 95 and 5, then we still get linear time. The actual problem isn't about whether I get a split that gives me n over 2, like in this case. The actual problem is when I get a split where the number of elements in one subarray is like a small constant, like 5 or 10, and I end up with a subarray of size n minus 10, or n minus 5, or n minus 1. It actually turns out that as long as I can guarantee that each subarray has a size that is expressible as a fraction of n, that I'm good. And I want to walk through how I can justify that. So what I will do is I want to solve this recurrence. Because we are used to solving recurrences that involve recursive calls that are T of n over something, I'm going to rewrite this. Now, this is, I actually went back and forth. I remade the slides a couple of times because I couldn't make up my mind about how to do this. So your mileage may vary. Basically, I believe the analysis is easier if we do it with n over something. So what I'm going to do is I currently have n times something. So I'm going to make up a number q equals this. Q equals 100 divided by 90. And then 90 over 100 times n is equal to n divided by 100 over 90, as I'm sure you can see. So I know that's weird, but it will result in our analysis being a little bit easier. One thing I want to remark about q, just before we go any further, is notice how q is greater than 1. That will turn out to be significant. And notice that if I chose some other value, so instead of 90 over 100n as my recursive call, suppose I wanted to do 99 over 100n, or even 999 over 1,000. Notice how if I compute q for those cases, that would be 1,000 over 999, which is still greater than 1. So any fraction of n, where the fraction itself is less than 1, will end up with q obviously being greater than 1, because q is just 1 over the fraction. Okay, so I have this recurrence where I've just subbed in my 90 over 100 for this value q, which is equal to 100 over 90. So I can do repeated substitution, which I do, and I end up at, so I'm just going to leave this here. You can pause and take a look at it if you want to try it yourself, but we know what repeated substitution is. I'm going to use our usual techniques. So we know by now that we're allowed to disregard floors and ceilings with repeated substitution and assume that n is a power of whatever you're dividing it by, as long as when you're done and you have a closed form, you verify that that closed form asymptotically is one of our usual suspects. So if it's somewhere between like log n and, and some polynomial of n, then generally we're all right. And of course, we can always write a formal proof later to verify that. If we solve a recurrence and get a value that's incredibly small, like log of n, or incredibly big, like 2 to the 2 to the 2 to the 2 to the n, then we have to maybe go back and see whether removing those floors and ceilings or assuming n was a power of q was a good idea. But as we saw earlier in lecture 8, I think, as long as we end up at the end with a closed form that is one of our usual suspects, it turns out we can disregard floors and ceilings with no problems. So I do this. At step I of my repeated substitution, I end up here. And then if I bring it home, so here's step I, and I realize that if to get rid of the recursive call, I have to set I to be log base q of n. And remember, q is greater than 1. So I do that, and I get this closed form. And if you want, as an exercise irrelevant to this lecture at the moment, you could prove this is actually the correct closed form. So go ahead and try that out. It's not so bad, really. I don't know if you believe me, but I don't think it's that bad. Anyway, what I want to do is I want to show that this closed form is actually linear. And I think I can do that. First, this term is log n, which means if this ends up being, and this is clearly constant, if the thing in the middle ends up being linear, then the log n sort of gets absorbed into that, and it's big theta of n. I think it's clear that this term in the middle is definitely at least equal to n. It's just that it's n times this strange summation, which isn't the strangest thing in the world. We've actually seen summations like this all the time in divide and conquer recurrences. I'm going to pull a technique out of nowhere for this. And the reason I'm going to do that is because I want to generalize this closed form to other values of q. You may notice that in my repeated substitution, I never actually use the real value of q for anything. None of this depends on q equaling 100 over 90. In a minute, I'm going to make an assumption that requires q to be greater than 1, but that doesn't mean q has to be 100 over 90. So my ulterior motive here is that I do actually want to be able to make a bunch of claims about any possible value of q greater than 1. Okay, so here's the technique I'm going to do. And I think you'll agree that this reasoning holds, even though this is a strange idea. I'm going to look at this summation here. And this is the summation C1n times a sum that goes up to log in base q of n all minus 1 and starts at j equals 0 of 1 over q to the j. And I argue that first, because the thing on the right here, q 1 over q to the j, is always going to be a positive number. So this will never be negative. Then I argue that this whole thing is less than or equal to c1 times n times this sum. Still going to be 1 over q to the j, and j is still going to start at 0, but I'm going to run the sum up to infinity. And I hope you can agree, yeah, this is definitely less than or equal to, assuming this summation converges to anything. It's weird to bring infinity into this because, aren't we all discrete math people here? Why are we talking about infinity? It's going to make my life a lot easier. So that's what I'm going to do. And I hope you can agree that it's pretty clear if I add more terms to the sum, it doesn't make the sum any smaller, so this inequality is valid. Okay, now observe this. We're going to reach back into our memory, into the distant past, into a calculus course, and recall that this geometric series converges to a constant for any value p greater than 1. So it's the series 1 over p to the j. The specific constant it converges to is something that I can't always remember off the top of my head, but I think it's 1 minus, in this case, 1 over p. But anyway, it turns out it always converges as long as the value of p is greater than 1. Now, notice how this summation looks a lot like that summation, except I've got q instead of p, and as I keep saying, q is greater than 1. That means that because this thing is definitely less than what I said a minute ago, which is the infinite series, starting at j equals 0 and of 1 over q to the j, and that converges to a constant, that means that I can treat this thing as a constant in my expression, which means this whole thing is big theta of n. Okay, observe that nowhere other than right here did I even mention that q was 100 over 90. And in fact, if I were to change the value of q, for example, to be 1000 over 999, this would still hold. That's a really big deal. What that's actually telling me is, and if we rewind a bit, we can see this. Actually, I'll just fast forward because it'll say it on the next slide. What this is telling me is that as long as my recursive call, so previously it was 90 over 100n, I was guaranteeing that the largest subarray has size at most 90% of n. It actually turns out that in this case, the algorithm would be linear. If I can choose a pivot that guarantees that the pivot is greater than 10% of things and less than 10% of things, then I'm good. But actually, even if I can only guarantee that the pivot is greater than 1% of things and less than 1% of things, I'm still good. Because in this case, the value of q would equal 100 over 99, which is greater than 1, and we would still get linear time performance. That's a really big deal. What that tells us is that this sensitivity that quicksort and quickselect pivots have, this n versus n squared performance, isn't really that sensitive to the division as long as you can manage a division that is a fraction of n. So 1%, 99%, 60%, 40%, 90%, 10%. As long as it's percentages of n, fractions of n, versus n minus something, then we're good. Then we get linear time quickselect. It actually turns out we could use the same type of analysis, but it would be a great deal uglier. We could actually show that In these circumstances, quicksort is actually n log n. So if we can come up with a pivoting rule that guarantees us a pretty modest guarantee, which is simply that p is less than 1% of things and greater than 1% of things, that's all we need. If we have that, Quickselect's linear, quicksort is n log n. So that finally allows us to tie off the loose end of, what's the matter with quicksort? So what do? We basically just need a pivoting scheme now. And I mentioned a couple of lectures ago that that's a lot easier said than done. Certainly, it's true that no constant time pivoting scheme is going to help us. That is, choosing the first element or the last element, or choosing 3 elements, or choosing a random element, or whatever. That's not going to make a difference. There are common quicksort pivoting schemes that try to avoid pathological worst cases. So I mentioned choosing 3 elements. One very common trick is to say, let's just choose from somewhere in the array 3 different elements, maybe from different places. So there's A, B, and C. And just figure out which one of them is the middle and choose that. That's still not going to work. We still could have cases where whatever pivot we chose, all but 2 elements are in the same subarray. So what we need, if we actually want to implement linear time quickselect, we have to find some pivot selection rule which guarantees that the size of L and the size of G are at most n over something at each step where Q is greater than 1. And also, of course, that choosing our pivot can be done in linear time. If it takes me n squared time to choose a pivot, well, obviously I've already lost the game. So all I want is a pivot that guarantees me any percentage of n. That's it. 1%, 0.5%, any percentage of n items will always be less than the pivot and always be greater than the pivot. So what do? Well, what I want, I guess, is to be able to guarantee that when I've chosen my pivot P, there is some small number of elements, but still a fraction of n. I don't care how small the number is, as long as it's a fraction of n, such that P is greater than this number times n and less than the same number times n. Okay, here's an idea. And this is coming out of nowhere, I guess. Suppose I choose a small number of elements out of my original array. So a small enough number that I can work with them without using too much time. Suppose I do n over 3. However, n over 3 is a random number here. I could do n over 7, I could do n over 5, whatever. I've chosen n over 3 for a couple of reasons that just to keep it clear of our next example. But n over 3 is just a made-up number. I just choose some small portion of my input array. Okay, so I choose a small sample of my input elements, and then there it is. And then I go and find the median of that n over 3 subset. So in other words, I find the thing that would appear in the middle if I were to sort it. And I wonder to myself, hey, how am I supposed to do that? Oh, right, aren't I in the middle of writing an algorithm to find medians? I mean, I could just recursively call Quickselect to find a median. Okay, that's a weird idea. Okay, so we'll hold that thought for a minute. Let's talk about what it means to be the median of this array. So this array has size n over 3. That means that if I look at the thing that would appear in the middle of that array when it was sorted, P has to be less than n over 6 things. And it has to be greater than n over 6 things. Wait a minute, n over 6? That's a fraction of n. That means that if P is based only on this small array, P is less than n over 6 things, P is greater than n over 6 things. That means that the size of L, when I look at my big array, has to be less than or equal to 5n over 6. And the size of G has to be less than or equal to 5n over 6. Now, notice that I should be using floors and ceilings. I should probably be saying something like this here. It turns out everything works out just fine, especially because I'm willing to do less than or equal to here. So I am conscious that I'm getting rid of floors. It's not making our lives any harder to get rid of them, and it turns out it's not changing our analysis when it comes down to it. And you could try verifying that for yourself later. However, in the proof I write in a few minutes, I will use the floor and ceiling functions. So don't worry about it. It's all going to come out in the wash. So what I've shown here is that if I just choose a small subset of the array, I can find the median of that, and then the median of that will give me a guarantee, because obviously, P has to be less than the things that come after it in the subarray when I sort it, so n over 6 things, and greater than n over 6 things in the subarray. And then I choose that as my pivot. So after taking this detour and finding a median of a small subset, I then bring P back around and use it as the pivot for my original array. Now this is weird. This is weird, twisty logic, because to find my pivot, I'm recursively calling Quickselect. Because Quickselect, of course, can be used to find medians. Okay, so I can expect that if I choose, let's say, n over 3 elements, although this analysis works perfectly well for any other number of elements, n over 7 or whatever, 3n over 8, but n over 3 is a convenient number for our purposes, then p will be greater than n over 6 elements and less than n over 6 elements, and that means that in the big array, L will have size at most 5n over 6, and so will G. So I end up with this, and then I hit a snag. So in my earlier analysis, what I showed was that, I'm going to hide that for a minute, what I showed was that as long as I have a recurrence whose recursive case looks like this, so for example, 99 over 100n plus some linear times stuff, as long as I have a recurrence that looks like this is actually going to be linear. That was the basic result of my last analysis. There was one thing I didn't plan for, which is I need to make a recursive call to Quickselect to find my pivot. I have to account for the time that takes. So even if I can guarantee that my pivot is going to be greater than and less than 1% of things, I now have to add an extra term to my recurrence relation to account for choosing the pivot. Okay, so to choose the pivot, I found the median of n over 3 elements, which means I had to call Quickselect on an input of size n over 3. So I end up with a second recursive term, and that's going to turn out to be a little bit of a problem for us. All right, so if I choose the median of the first n over 3 elements, and again, the math works out pretty much the same way no matter what size of subset I choose. If I choose the median of the first n over 3 elements, then I do guarantee that the largest subarray I end up with has size 5n over 6. However, I have to add a recursive call to account for finding the pivot, so t of n over 3. Now, it turns out that when we do this, everything goes haywire, and that we end up with if we found a closed form for this, it would not be linear. It would be something else. It is not pleasant to find a closed form for this, because when you have two recursive calls and you do repeated substitution, it makes a huge mess. It turns out that the recurrence, that if we were to solve it, the value of t of n can be proven to be definitely bigger than n log n. One way of proving this, if you want to do so, we're not going to write the proof right now, although this is actually a very useful proof to write. It's not a big deal. Like, it doesn't take too long, but it helps to build some dexterity with working with weird recursions, weird recurrence relations, the kind of weird thing that might show up on an assignment or exam in someone's course. You could write a proof like this, and you can see if I can prove that t of n is always greater than or equal to n log 3 of n, clearly it's big omega of n log n for whatever base you'd like to choose. It actually turns out that t of n, notice how I didn't say big theta, I said big omega, because I was able to prove to myself, like I wrote a proof that it's big omega of n log n, and then I thought, that's all I need to know. It appears to be even bigger than that, but I don't care. All I care about is it's clearly too big for comfort. I want to justify sort of, I guess, intuitively what the problem is. Okay, so notice that I'm making two recursive calls. Let's count how many total elements I'm recursing onto. So the first recursive call recurses into 5n over 6 elements. The second one recurses into n over 3, but n over 3 is 2n over 6. And notice that if I add together those two recursive calls, I'm apparently recursing into 7n over 6 elements, and 7n over 6 is greater than n. So unlike our typical recursive case, where the things we recurse into overall are either equal to n or less than n, here, when I go down one level in recursion, the linear time component ends up being greater than what I started with. And you can see that means it's going to sort of balloon outwards as I go further and further down into recursion. That's my problem. There's actually nothing wrong with the idea of making a recursive call to find the pivot. It's just that the combination of the size of my recursive call, n over 3, and the guarantee that I get about the size of the size of L and G, those two things don't quite fit together perfectly, and I end up getting something like this. And this is a bit alarming. So that means the number of elements I process as I go down one level of recursion is larger than the number I started with. It still actually ends up being, I think it is a polynomial time thing, like t of n is big theta of n to the 1 point something, but it's still obviously pretty alarming, and it's not going to give us the linear time algorithm that we want. For contrast, let's just think about recurrences that don't have that weird behavior. So for binary search, or for the best case of Quickselect, t of n would be t of n over 2 plus, I don't know, plus n. For merge sort, or the best case of quicksort, t of n equals 2 times t of n over 2 plus n. well, plus n plus some stuff. Notice how in both cases here, the total number of elements I recurse onto is n over 2, which is obviously smaller than n. So I can expect as I go down through layers of recursion that the number of elements will be whittled away pretty quickly. Over here with merge sort and the best case of quicksort, the total number of elements that I recurse into is, well, 2 times t of n over 2, or at level 2 of recursion, I'm going to have 2 branches that are each n over 2 in size, or n in total. So total number of elements as I go down through recursion is the same. It's n at this level, and n at the next level, and n at the level after that. It's always n. And if I sort of write out like a tree, if I say, okay, so t of n, in this case, I call t of n over 2, and then I call t of n over 2, because there's 2 recursive calls for quicksort. Each of those gives me an n over 4. Notice how if I add up the total number of things at each level of recursion, I get n. And that's fair enough, because I know that there's only going to be log n levels of recursion, and there are n things at each level, which means that I get a running time of n log n. Whereas with this, I actually get a decreasing number at each level, and there are log n steps. And it turns out it just works out to be log n. But with this recurrence, it ends up being larger at each step. I actually have more, as the further I go down in the recursion tree, the more things I have. So that's nasty. Now I've just spent more time than I ought to talking about this recurrence, but I think it's an interesting case to talk about when we see it, because we don't see it very often. And it's interesting how things sort of fall apart when you end up with this case where as you go down through recursion, the number of elements gets larger. I really want to emphasize, though, that the problem isn't the recursive call to find the pivot. There's nothing wrong with doing that. I just have to be very careful how I do that. I also will observe, so this is pointing out the thing I already mentioned. This second point is observing that it doesn't actually matter if I did n over 3. I would get the same problem. If I did n over 7, I would actually have the same issue, but the math would be a little bit less pleasant. So if I did a subset of size n over 7, I would end up with something like this. T of n over 7 there, and here would be something like t of 13n over 14, and I would still have the same problem, because this is 2 times n over 14. And we would then end up with 15 over 14n, which is greater than n. So it doesn't matter whether it's 1/7 or 1/3 or 3/8. We have the same problem that shows up no matter what we use. It's still potentially viable to do a recursive call to find the pivot. We just have to make sure that if we add up the total number of elements between the 2 recursive calls, it ends up being less than n, basically. So it could be proven, I mean, this is just a sample, but it could be proven, for example, that if I chose to recurse on a subset of size n over 12 and still managed to get a guarantee that p was less than 1/6 of things and greater than 1/6 of things, then this would be the recurrence, and it turns out this does work out to be big theta of n. We could actually prove that. So it's not the second recursive call that's causing the problem. It's specifically the way that the 2 sizes sort of articulate together. That's the problem. So I guess what this is telling us is that if we can find a pivot selection scheme that might use Quickselect recursively, but manages to use a bit more leverage or something, so that is, it's able to recurse on a very small subset, but still get a robust guarantee, if we can do that, I think then there's hope. Then we might get our linear time algorithm. And here's the place where I sort of have to pause and say, I like my usual approach to this is, let's just do some thought experiments and see if we can come up with something. Like, see if we can ourselves derive the algorithm that we want. And I feel like, we did with merge sort and quicksort. If we talk about the merge and split process, we can sort of come up with quicksort ourselves from scratch. And same thing with Quickselect. We were able to engineer Quickselect by looking at quicksort. However, for this pivot selection scheme I'm going to discuss, I have no idea how you would invent it from scratch. It feels like it was invented by a bunch of experts and they probably took a long time to do it. And it's the kind of thing where it's good they had their inspiration, because it's a very weird strategy that they use. And it's called, I'm going to call it BFPRT pivot selection. It's named after its authors, which are Blum, Floyd, Pratt, Rivest, and Tarjan, which is a who's who of famous computer scientists and famous algorithms people. I've mentioned before that I'm a bit wary about naming things after people, because sometimes just because something is named after a person doesn't mean that person invented it. This is a case where I think it's pretty clear cut that these people did invent this algorithm. They all published one paper about it, so it's pretty clear that they all agree that they all deserve credit for it. And the algorithm itself is so strange and so specific that I don't think there's a risk that somebody else already invented it, because it contains all these weird details that are so specific that I can't imagine somebody else having already invented them before. And it's going to be a really weird strategy. So our goal is to understand it, and it's so specific that we don't really need to ever use the insights from it anywhere else. It's not like we have to later adapt this to some other strategy. So our goal is just to understand this as, masters at work, people that came up with an algorithm to solve a really sort of thorny problem in a really clever way. So here's the idea behind BFPRT pivot selection. At each step, we take the entire input array, so we have this big array A, we take the entire thing up and we chop it up into pieces of 5 elements each. And yes, 5 elements, not 3, not 4, not 9, 5. It turns out it's possible to use larger subsets, so I could do 7 or I could do 9, but I'm not allowed to use subsets that are smaller, so I can't make subarrays of size 4 or size 3. I mention that because when I first saw this algorithm, I was completely baffled by this size 5 business. I was like, wait a minute, I'm a computer scientist. I like, powers of 2, or if I can't work with a 2, I'd like a 3, please. I don't want to see a 5. 5 is a weird number in the context of algorithms. Where did you get a 5 from? It actually turns out that if we were to do this whole thing with subarrays of size 3, then it wouldn't work. It actually has to be size 5. Additionally, for reasons that'll become clear in a minute, it's very useful that the array size be an odd number. That's actually critical. If it's an even number, it makes a bit of a mess. So the smallest odd number we can work with turns out to be 5. Okay, so what I do is I take my input array and I chop it up into pieces where each piece contains 5 elements. Now, obviously, your next question should be, wait a minute, what if the input array is not, the size is not a multiple of 5? So what if you give me an input array of size 117? Okay, in that case, or 129. In that case, it is permissible to chop off a couple of elements until you get back to a multiple of 5. So here I could do the first 115 elements and ignore the others, and here I could do the first 125 elements and ignore the others. Notice that if I do this, I'm throwing away at most 4 elements, which turns out not to be a big deal in the grand scheme of things. So what I'm making are the floor of n over 5 subarrays, and just ignore the remainder. Okay, now, what I'm going to do is take each of my subarrays, which all have size 5, and independently, so I'm only going to work with one subarray at a time, I'm going to sort their elements. And I told you this was going to be weird. So I then take each of my arrays of size 5 and sort them. And here I'm going to leverage a weird loophole in algorithm analysis. This is completely above board, but it just feels strange, which is I am sorting an array here. And it feels like sorting is a difficult problem, right? Especially given that we're trying to do selection, which is an easier problem. I'm sorting an array of size 5. 5 is a constant. All of the arrays have size 5. They will always have size 5. Sorting an array of size 5 requires constant time. I mean, let's think about it. So even if I use a really bad sorting algorithm, one that takes n squared time, well, if n is 5, is 5 squared, and 5 squared is 25, and 25 is a constant, which means I can sort arrays of a constant size in constant time. That means if I want to sort each of these n over 5 subarrays, then it actually takes linear time. I just go through each subarray once and sort it, and the sorting itself is constant. So that's weird, but it's valid. I can sort each of my subarrays separately, of course, in linear time overall. Okay, once I've sorted my subarrays, now on the slides, I visualized them sorted from bottom to top. So as you can see, the smallest elements on the bottom and the largest elements on the top. Because my subarrays have size 5, which is an odd number, there is exactly one unambiguous median element in each subarray. So just to recap what I've done so far, I've taken my array, split it into pieces of size 5, and then I've sorted each piece. And now, if I visualize it like this, notice how it's very easy for me to pull out the median of each subarray. And if I look at this, if I treat this like a sequence, the sequence of medians, it contains n over 5, well, floor of n over 5, but I'm just going to say n over 5 values. So now I have a subarray of size n over 5, and it consists of the median of each of my smaller arrays of size 5. Okay, The next step is just a visualization thing. So I'm going to call it a thought experiment, and we'll see in a few minutes how I actually implement this. What I'm going to do in my next step is I'm going to take my set of subarrays of size 5, and I'm going to sort them from left to right based only on their median. So I'm going to look only at this middle value, and I'm going to rearrange the subarrays from left to right. In other words, this one has the smallest median, 27, so it's going to come first. This one has the largest median, 77, so it's going to come last. There's my thought experiment. So I sort my subarrays by their medians. I'm not actually going to do this in my algorithm. I'm going to do something a bit faster. But I just want to illustrate something, so I want to rearrange them into sorted order. Okay, so I use the median to sort them into ascending order by the median. Now I notice this thing in the middle here, this 52, is right in the middle of my sequence of medians. And so actually, because I sorted these subarrays by their median, and 52 is now the median of that, we're going to call it the median of medians. And I'm going to give it, let's call it P. That might be significant. So I call this value, this median of medians, P. And I want to make some observations about what I can say about 52. Okay, so first, 52 is the median of this middle row, which means it has to be less than all of those things, greater than all of those things. We'll say these things are less than P, and it has to be less than all of these things. These things have to be greater than P. How many of them are there? Okay, so we know that the row itself contains n over 5 things, which means that, and 52 is in the middle of it, which means that if I look at about half of the row, the first half or the second half, each half of the row contains more or less n over 10 things. So that would be n over 5, so to be clear here, n over 5 all over 2, which is just going to be n over 10 things. So we can be guaranteed that our value p is greater than n over 10 things and less than n over 10 things. Okay, but that actually isn't really that exciting because our earlier approach gave us a similar guarantee. But we can do even better. Notice that each of the elements over here, these are all medians of an array of size 5, which means that these things are greater than everything below them. Okay, but how many things are below them? I already said that the number of things over here is going to be n over 10 things. And I've got 2 rows, because I have arrays of size 5, it'll always be 2 more rows below it, which means if I look only at this lower left quadrant, this has to have size 3n over 10. At least. I can also say that I also want to include in the quadrant these elements, because 52 is also greater than elements in its own subarray. Similarly, 52 is also going to be less than everything up here in the upper right corner, and there have to be 3n over 10 things there as well. There are n over 10 things here, and then there are going to be n over 10 things and n over 10 things there. So we already know 52, our value p, is greater than the n over 10 other medians and less than n over 10 other medians. But going further, because each median is greater than 2 elements and less than 2 elements, p is greater than 3n over 10 things, and it's less than 3n over 10 things. And remember that, yes, this is 3n over 10 with a floor, not actually the number 3n over 10, because we have to accommodate both the nuances of the division process, because the size of the array may not be amenable to division by 10, but also the fact that p itself is not included. And so what I can now say is that means that once I exclude p, because p has to fall into the subarray E, I can now say that because p is greater than or equal to 3n over 10 things and less than 3 over 10 things, that means that both L and G must have size 7n over 10. And that's a big deal because if I work backwards and think about what I needed to do to choose P, it turns out the only recursive call I need to Quickselect is this step here. So remember back when I sorted my subarrays for the visualization. I went from my list of medians to arranging the subarrays in order by their median. I told you I don't actually need to sort the subarrays because all I care about is getting the number 52. In other words, what I'm doing at this step is I'm taking the set of medians, and there are n over 5 of them, and I'm finding the median of it. I'm finding the median of medians. And that requires a call to Quickselect, and the recursive call takes time t of n over 5. Okay, so this is a weird technique. And as I said, the first time I saw this, I had no idea what was going on. And I will admit that probably the only time I felt like I truly had my head around this was the first time I had to teach it. So a million years ago when I was like teaching a lab or something for an algorithms course, and it was about this, and I just had to sit and stare at it for hours until I was sure that I knew enough about it to answer questions, and then just hope that nobody had any questions that day. Because it is just a truly bizarre algorithm in a lot of ways. Okay, so what I've done is I found this pivot P by sorting my subarrays in linear time and then finding the median of medians. This median of median value 52 can then be my pivot, and it's going to be less than, it's going to guarantee that the size of L and the size of G is going to be at most 7n over 10. All right, computing the sequence of medians that I ended up finding 52 as the median of, that required linear time. I just sort each subarray in constant time, and that takes linear time over all the subarrays. Finding P then requires a call to Quickselect on n over 5 subarray medians. So we get this recurrence here. And it's our usual style of recurrence. Just like before, we now have two recursive calls. I do a recursive call on the largest of L or G. I also do a recursive call to find the median of medians, P. And then I've got my linear time stuff from before. Notice that in this case, if I look at the total number of elements I'm recursing onto, so I've got 7n over 10, more or less, plus, so n, floor of n over 5 would be 2n over 10. That's going to equal 9n over 10. So unlike our earlier example where we had an issue where they came to be larger than n, this is less than n. So when I go down one layer of recursion, I am now working with fewer than n elements. And that turns out to be the critical step. I want to do an actual analysis and finally write an actual proof. I'm going to do that by cleaning the recurrence up a little bit. So what I'm going to do is basically, I'm going to make a new recurrence called t prime, and it's going to be pretty obvious that t is less than t prime. And then I'm going to show that t prime is less than 10 times cn, where c is a constant I'll define in a minute. You could see hopefully that because I'm showing with less than signs, as long as I can show that, as long as it's obvious that t is less than t prime, any result I prove about t prime will apply, I can work it backwards into t. The reason I'm going to do this is just to avoid some annoying semantics, I guess, because I would really like it if I don't have too much constant junk lying around. That's pretty much my issue. So what I'm going to do is I'm going to make t prime basically by condensing all the constants in t down into one thing. So let's make a new constant just called c. It's going to be CB plus C1 plus C2. Notice that that means that CB is definitely less than or equal to C. So if I put C in T prime is greater than or equal to T. Additionally, I don't like this C1n plus C2 because there's just lots of stuff to juggle and it's going to make a very unpleasant looking closed form. And it's going to result in the induction proof requiring some special cases. So what I'll observe is, notice how this only shows up in the case where n is greater than or equal to 2, which means that if I wrote C1n plus C2, that's obviously less than C1n plus C2 times n. And in turn, that's obviously less than C1n plus C2 times n plus CB times n, because of course in algorithm analysis, we assume all these constants have to be positive. Like there's no way they could be, that it makes no sense for the base case to require a negative amount of time. Although if you ever discover an algorithm that requires a negative amount of time in some cases, please just send me off a quick email about that. I'm interested in finding out about such a thing. So what I'm doing here is just replacing, I'm just saying, let's just replace this with c times n, keeping in mind that as I was able to justify, it's obviously going to be, this is obviously less than or equal to c times n. So I end up with this recurrence t prime, which will be a bit cleaner to talk about if I want to write a proof. And the proof I want to write is simply that t prime of n is less than or equal to 10 times cn. And we know that c is a constant, so this is enough to establish that t prime of n is big theta of n. My proof is going to be by induction on n, and it's going to be frankly pretty straightforward. So when n is equal to 1, okay, well then t prime is just equal to c, and n is equal to 1, so that equals cn. And I guess I didn't write it here, but hopefully it's clear to you that c times n is less than or equal to 10 times c times n, so the claim holds. Actually, you know what? I probably should have written 10c. I should have put that in the line. I know it's obvious, but because one of you might one day lose a mark for not doing that. Just to be clear, I'm deducting a mark for myself for not writing that in, even though it's maybe obvious to some readers. Now, my hypothesis, suppose that t prime of n is less than or equal to 10cn for every value n in the range 1 through k for some value k greater than or equal to 1. Notice how this value k does intersect the basis. And I'm using a stronger hypothesis here because I have to be prepared when I divide in my recursive calls to resort back to a lot of previous values. And then, frankly, the rest of the proof is relatively straightforward algebra. So I consider t prime of n plus 1, and I expand that out, so I write these things out in full for the case where I'm working with n plus 1. By the hypothesis, because we know that both of these recursive calls are on smaller things, by the hypothesis, this whole thing, okay, I should put I've hit 2 typos for this proof. That should say less than or equal to. By the hypothesis, this recursive call is less than or equal to that, and this recursive call is less than or equal to that, so I can get to this step. And what I'm going to do next is I'm going to observe that obviously a floor function doesn't make things any bigger. So what I can do is just remove the floor functions, and then I end up with something that is, so with the floor functions, this is less than or equal to the version without the floor functions. I've also put the two things on a common denominator, and then I just cancel out the tens. And I end up with this line here, which is less than or equal to 7cn plus 1 plus 2cn plus 1 plus cn plus 1, which is 10cn, and that's what I'm looking for. So the claim holds for n plus 1, and by induction, I can now say that t prime is linear for n greater than or equal to 1. And that's enough to show that t is linear, which means I have found my linear time Quickselect. And here it is. Here is the full pseudocode for Quickselect with BFPRT pivoting. And I'll take this opportunity just to show off like the full context of what I was talking about before. It's interesting because really now, because my pivot selection scheme has been exported to a separate function, I've got this neat sort of mutual recursion pattern happening. Although you could argue this is just a utility function and therefore I could just paste it directly into there. But it's still a neat design, a pattern to see in the implementation. Okay, so you give me an array A and you give me an index K. I'm going to have my base case as usual, and then I'm going to call my BFPRT pivoting function to find a pivot, and then do the rest of Quickselect as before. Now the pseudocode looks a bit different just because I've had to adjust the length of lines to fit in this other pseudocode. Now, over here in my pivot selection rule, what I do is I get the length of A divided by 5, so T is the number of subarrays I'm going to want. I then partition A into T subarrays, and I'm not going to bother explaining how to do that because it's pretty clear how we partition things. That can be done in linear time. And I think the slides are going to do a nice green highlight for me there, yes. So I can do this in linear time. Okay. And then I sort each subarray. So I'm actually sorting n over 5 things. So that's going to take linear time, but each sort operation is constant because the subarray size is constant, which means this entire step is big theta of n. Now, what I've done here, remember, I've had to keep justifying this. I've said over and over again that sorting the subarrays is constant time. And I've done that just so that I could earn the privilege to write sort each subarray as part of my pseudocode. Because we've seen before, I'm not allowed to hide complexity in pseudocode by writing something that sounds innocuous. If I just say sort each subarray, it's obviously up to me to prove that that's going to take linear time overall. I can't just say it and say, oh, you can go find a way of doing that yourself. So in exchange for writing sort each subarray, I have had to keep saying that sorting at one subarray is constant and there are n over 5 subarrays in total. Okay, so I've done 2 linear time things. Now I make, just for the sake of, there are ways around having to do this directly, but for our purposes, it's easy to do it this way. What I do here is I make an array of length t, and then, so this would be my array of medians. And actually, I think the iteration here is to start at 0, not at 1. And then I just copy in each element of my array of medians is going to be the ith subarray's median. So of course, the subarrays have size 5, which means index 2 will be their median after I've sorted it. And then, to get the pivot, I just call Quickselect on that. And I ask for index t over 2, which would be the middle of this array of medians, my median of medians. And that's my BFPRT pivoting procedure. It's really bizarre, but it does do the trick. Additionally, if I were to take that pivoting procedure and plug it into Quicksort, I would actually get a n log n Quicksort implementation. And so the question is, way back on our character select screen in lecture 9, why didn't I list Quicksort as having the worst case n log n running time? And the answer is, like I said back in lecture 9, we don't view this thing to be ordinary quicksort. We view this to be some advanced variant of quicksort, some extended edition of quicksort. And in practice, if somebody goes to implement quicksort, they don't do this. Because the reason that we would like quicksort, as we saw with the timing experiment, the advantage quicksort has is that quicksort is very streamlined. It requires relatively little work overall for most of its steps. The split step is simple, the merge step is simple. So quicksort in practice tends to be a little bit faster than merge sort because of that streamlined nature. If you plug in the BFPRT pivoting scheme, it just sort of falls apart. Because notice how to compute the BFPRT pivot, I have to do a whole ton of extra work, tons of work, and I even have to call Quickselect. So that is, if I want to use BFPRT pivoting with quicksort, I have to keep around this algorithm and an implementation of Quickselect, which is of course itself recursive. So that means that although quicksort ends up being n log n in this case, it's a bit of a Pyrrhic victory. It is n log n, but it's so slow because of the machinery needed, it's got so much constant time overhead that it's just not worth it. And in fact, while we're on the subject, although Quickselect is linear time asymptotically, when you use BFPRT pivoting, it usually isn't worth it even to do that, because BFPRT is so resource intensive in a constant time sense, it's doing a lot of extra constant time work, that Quickselect ends up being pretty slow. If instead you use the ordinary Quickselect, which could be n squared, and shows, I don't know, like a random pivot or something, and remember that using a random pivot gives us some insulation against worst cases, except if we're extremely unlucky. Normally, when Quickselect is used in practice, it probably is just used with a randomly selected pivot and without bothering with the whole BFPRT procedure. Which means, in a sense, maybe BFPRT's main benefit is as a theoretical curiosity, as something that demonstrates that selection can be done in linear time, even if it's not always practical to do so. So it's still a very useful result, but it's a result that arguably is more often seen in algorithms courses than it's seen in any other context in an implementation sense. It's often also seen in other contexts where algorithms are discussed because selection could be a component of some other algorithm, and in those cases it's very useful to observe that selection is linear, but yeah, maybe it's more of a theoretical thing than a practical thing. Okay, fair enough. Well, I guess that means that we should spend our next lecture talking about something, a more purely practical technique. And since we spent all of this lecture coming up with a fast algorithm, maybe we'll spend the next lecture talking about, slow algorithms.